Hi everyone, I'm Jill. I'm a PhD student from UCLA. Today I'll present our work, Relax, Compensate, and then Integrate, which is about doing fast approximate probabilistic inference with logical and algebraic constraints. Specifically, it's about probabilistic inference on hybrid domain, which basically means that we have both continuous and discrete variables. We also have complex constraints, which are both logical and algebraic ones. To perform probabilistic inference in these scenarios, we will first show that it is infeasible to have an efficient and exact solver for general problems, and further, we propose a fast approximate inference algorithm for this purpose. To start with, let me convince you that it is important to model both continuous and discrete variables and constraints. Consider a skill matching system for online games. You have to model several players. And for each player, he or she has a certain skill, which is a continuous variable. And these players can form teams. So there are intricate dependencies between these variables. Moreover, to model the team performance, we need to introduce some constraints saying that the team performance is a result of aggregating the skills of players in the team. And finally, to better describe the team performance, we also introduce discrete variables to indicate whether players in the same team are friends or not, which we call the squad, because usually the team would have good performance if players know each other. And given such a scenario, you may want your system to answer such a question. What is the probability of Team 1 to outperform Team 2 if Team 1 is a squad while Team 2 is not? So in this scenario, we just described, we need to model both continuous and discrete variables and constraints over them. Now the question is, which probabilistic model can we use? Can we use the popular GANs or variational autoencoders? No, because they have limited inference capability and they're not able to deal with constraints. Then what about classical PGMs like the hybrid Bayesian networks or mixed PGMs? Nope, because they are limited in representation power. They have strong distributional assumptions and cannot deal with the constraints. There are more recent tractable probabilistic models, like the tractable probabilistic circuits, but still no, because they cannot deal with complex hybrid domains, hybrid constraints. So instead, we use satisfiability modular theories, or simply SMT. It is a generalization of the set language and is a representation language over the linear real arithmetic that allows us to have constraints over both continuous and discrete domains. It delivers all the ingredients we need by design, and it is also widely used in robotics, verification, and planning problems. Let's go back to the previous scenario to see how to model the skill matching system with SMT. So for the skill of each player, we introduce constraints. So this constraint says that the skill is a continuous variable bounded between 0 and 10. Then for the team performance bounded by the player's skills, we also introduce constraints. This constraint says that the team performance xt is a continuous variable bounded by all the players in the team. And next, for the squad, to indicate whether it is a good team or not, we can introduce a Boolean variable BS here. And this constraint says that if the team is a squad, then the team performance xt is boosted. When we bring all these constraints together, what we obtain here is a single SMT formula in conjunctive normal form, describing the skill matching system. To further abstract variable dependencies in an SMT formula, we could derive a primal graph for the formula. So in the primal graph, the nodes are variables in the SMT formula, and there is an edge connecting two nodes if the two variables are in the same class in the SMT formula. An SMT formula, however, does not model uncertainty, but we can make it probabilistic by defining a certain positive functions called weights associated to the models of a formula data. An SMT formula together with these weight functions forms the weighted model integration model. We can think of this model as a distribution whose support is defined by the SMT formula and density defined by the weight functions. Then the task of weighted model integration is to compute the partition function of the normalized distribution. So here is the formal definition of weighted model integration, which we call WMI. Given an SMT formula and the associated weight functions, the task of weighted model integration is to compute the big integral shown here. Intuitively, what it does is to integrate over the weighted volumes of the feasible regions defined by the formula. Now let's go back to the aforementioned question that cannot be answered by the other models. What is the probability of Team 1 to outperform Team 2 if Team 1 is a squad but Team 2 is not? It's easy to answer it within the WMI framework. We first introduce two constraints here. The first one describes the condition Team 1 is a squad and Team 2 is not. And the second one describes the query, that is, the performance of Team 1 is better than Team 2. Then the conditional probability would be the ratios of two weighted model integration. It tells us that in this case, Team 1 that forms a squad wins with probability around 58%. And now the question is, how hard it is to compute the integral in the WMI task. Next, we will show some theoretical results about this. First, computing the WMI in general is sharply hard, since it involves solving an arbitrarily complex integration problem in high dimensions. Our previous work showed that for WMI problems with tree-shaped primal graph and for weight functions that satisfy some tractable weight conditions, there exists an algorithm that can do inference in polytime. And we call the tractable WMI class in the previous work as tree WMI. And we put these problems in our graph here. This is the largest tractable class known so far. And now the question is, can we expand this tractable class, for example, by slightly increasing the tree width? The short answer is no. We proved that for the WMI problem class parameterized by tree width, the problem class is tractable if and only if the tree width is 1. That is, even a slight increase in the tree width could result in sharply hard WMI problems. So this implies the fast approximation for general WMI problems is much needed. Therefore, we introduced ReCoIn, an approximate WMI inference algorithm that works on intractable WMI problems. Now we show how ReCoIn works. Recall that for each SMT formula, we could define a primal graph to describe the variable dependencies. For the WMI problems with loopy primal graph, we're going to do approximation by relax compensate and integrate scheme. First, we relax the problem into a tractable one by adding copies of variables and literals. Here we make a copy of the variable xp2, substitute the copy into the dependency between variable xp2 and xc2. The dashed edge in the graph represents a removed dependency, and the red edge represents an equality constraint. So far the problem has the same complexity as the previous one. And then we also remove the equality constraints, resulting in a loop-free problem. In other words, we break the loops by removing the variable dependencies. However, simply removing things will not bring good approximations. So next, we compensate for the removed dependencies, specifically the equality one, by introducing certain literals and parametric weights. And this is done by optimizing the weights iteratively by solving a series of exact integration problems, with this optimization goal being matching the marginals between a variable and its copy. This implicitly compensates for the equality constraints. We compare ReCoIn with other existing approximate WMI solvers on synthetic benchmark. So in the figure on the left side, we compare the accuracy, and in the figure on the right side, we compare the inference time. For the results, we can see that ReCoIn better scales to larger WMI problems than more sophisticated WMI solvers, while still delivering accurate approximations. To conclude, real-world data is noisy, complex, and mixed continuous discrete. The WMI framework is very appealing for probabilistic inference in the real world. Efficient approximations are not only useful but needed. And our proposed solver ReCoIn is able to deliver fast approximate inference. What's next is that we would like to explore its application in program verification, probabilistic logic programming, etc. And any questions are welcomed. Thanks for your time.